In this sixth video on directional properties of crystals, I'll use the elasticity of Plagioclase series feldspars to illustrate the properties and manipulations of tensors that we have been discussing in the prior lectures. So Plagioclase elasticity, much of this comes from a paper published and to be published by Brown and Angel. And the photomicrograph shown here is of a felsic rock. The materials in the rock are primarily feldspar. The plagioclase minerals may make up as much as 60% of the mid and lower crust, continental crust, and certainly a large fraction of the oceanic crust is plagioclase feldspar. Feldspars ubiquitously twin in a polysynthetic way, and the Albite twin law is a common twin law. You can see in this photomicrograph a single domain of a plagioclase crystal with multiple twins. The alternating pattern of light and dark represent alternating twins within a plagioclase pseudocrystal. So individual plagioclase crystals are almost always twinned. They're almost always twinned, showing a laminar pattern such as this, with the b-axis perpendicular to the striping that you see on the crystal. So throughout this picture, you see polysynthetic twinned domains, and they are preferentially aligned such that all the B directions tend to line in a general direction, while the A and C axes of the feldspars tend to form a girdle around the B. Now, there has been work on the elasticity of feldspars, and it dates back to Rysova in 1964. And here is a set of plots of data published by Rysova, and the symbols represent a handful of points measured on not single crystals of feldspars, but rather polysynthetic twinned aggregates. Now, with that typical twinning pattern, the crystals have a pseudo-monoclinic symmetry. Now, Rysova and co-workers measured 6 compositions between anorthite 9 and anorthite 58. Now, on each crystal, they measured 6 propagation directions and 3 acoustic wave polarizations. That's a total of 18 observations. Now, since monoclinic crystals have 13 elastic constants, they believe that their 18 observations overdetermine the 13 unknowns. They made no error analysis at the time, but they suggested that there was an experimental precision of about 1.5%. They noted some data scatter, and I'll claim that the data scatter is 5%, and the misfit is as large as 10%. The lines in the diagram represent their fit to the elastic constants, and actually the dashed line, long dashed line, represents an alternative fit published by Alexandrov in the early 70s. They attributed their misfit to cracks, pores, and imperfections and orientation errors in their samples. Mind you, these are not single crystals, but rather an aggregate which may have cracks opened up along cleavage planes. So there's been long-standing concern that these results, first of all, have not been reproduced by others, and there has been a continuing observation that if you looked at the results directly, they seem to favor a particular way of averaging elastic constants, which I'll talk about later. And they also suggested that more modern rock measurements of velocity might be inconsistent with these single crystal or pseudo single crystal properties of the feldspars. Let's talk a little bit about feldspars, and I have an animation at the bottom from Bob Downs. I'll get to that in a moment, so don't let that distract you. Let's put in some coordinate system here for the plagioclase minerals. Let's put in a b-axis parallel to the y crystal or y Cartesian coordinate system, and align the x-axis coming out of the screen and the z-axis oriented vertically. For albite, the c-axis is inclined as shown here, and let's put that c-axis in the yz plane. So the c-axis is tilted relative to the b-axis by an angle of 94 degrees. And here's the a-axis, which is tipped down at a distance of 117 degrees from the c-axis. Now this a-axis is not quite in the plane of z and x. In fact, the angle to the a-axis is 88 degrees from the b-axis. So this is not an orthonormal coordinate system. This is what you expect for triclinic axes. Within the structure of the plagioclase feldspars, you can find what has been termed a crankshaft chain of silica tetrahedron arranged in fourfold rings that are joined together, shown there. The crankshaft comes from the idea that you can draw a zigzag line such as this through these fourfold rings. Now, if you squeeze along these chain directions, which are aligned along the a-axis, you can imagine that those chains can compress fairly easily, since there are large gaps in the structure that can be accommodated by, and so this compression can be accommodated by simply changing the angles between the segments of these rings. Let's see if I go back down here and get this to run again. At this point you can see, let's see, and I think I add in, okay, there, the response to pressure. So if I start playing it now, you can see that in the horizontal direction, which is aligned with the x-axis coordinate system, that there is a fair amount of compression as the crystal is exposed to hydrostatic stress. In contrast, there's less compression along the vertical direction, or the in and out of the page direction. And if you look carefully at this animation, you can see that the angles between the silica tetrahedron are being distorted by application of hydrostatic stress. So all of this would suggest that there could be very large anisotropy in elastic properties of the feldspar structure. Well, now there's a question: why study the full anisotropy of the feldspars? Why? Well, the starting point is that in fact there are no natural large single crystals of feldspar. They're always ubiquitously twinned, and they exist in rocks in either random or some preferred orientation directions. So why study it? Well, there have been questions about the pseudocrystals studied by Rysova, and in fact these were rocks rather than crystals, and so there's the suspicion that cracks in grain boundaries might have biased their results. Note that there's a cleavage on the 001 and 010 directions. So the existing data may not be representative, and if we're going to use the data to estimate rock properties, we need a better data set. Furthermore, it's intrinsic interest in the physics of the crystal by getting all 21 elastic properties. Reminder of chemistry within the feldspar series. Along the bottom we have the sodium to calcium feldspars, the plagioclase, with only a small amount of solid solution of potassium. And then along the left-hand side, between albite and orthoclase, we have the alkaline feldspars with relatively low solid solution of calcium. In the data I will show, we have a series of compositions stretching across the plagioclase series. Plagioclases are complicated, and this phase diagram gives some indication of variations of structure. It's not a homogeneous crystal structure all the way from albite to anorthite. So there's, in big picture, there's a C-bar1 structure on the albite side, which extends up to about half anorthite composition. On the anorthite-rich side, there's an I-bar1 structure and a P-bar1 structure at the very highest amounts of anorthite. As the temperature is lowered, you go from liquid to a structurally disordered, that's aluminum disordered in the silica tetrahedron phases, and then as you drop temperature, it re-equilibrates to ordered arrangements or low feldspar structures. So our samples spanning across here, first of all, range within the albite C-bar1 range of structures, and these are principally low albite, fully ordered aluminums. Then we have a series that are in the I-bar1 and P1 structure with higher anorthite composition, and in the intermediate range there's some more disordered structure showing up, as well as some intergrowth between the C-bar1 and the I-bar1 for the intermediate composition. So now, triclinic elasticity. Remember, in the general case we have 21 elastic constants. In the monoclinic symmetry there are 13 elastic constants which apply for this pseudo single crystals if twinned. And then I'm going to mention transverse anisotropy, in which a girdle of A and C directions are associated with a preferred direction for the B-axis. This gives 5 elastic constants if the B-axes are nearly aligned with the A and C girdle in the equatorial region. These measurements were taken using impulsive stimulated surface waves. On polished samples, we set up standing surface waves of well-defined wavelength. As I showed in the last video, these are time domain measurements that are Fourier transformed. The velocity is given by a frequency times a wavelength, and the accuracy is better than 0.2%. For each composition, we typically use 6 polished surfaces oriented in different crystallographic directions. We had, on average, about 125 directions for each composition, and that gave us about 163 observations of Rayleigh and pseudo-surface wave velocities. Okay, let's talk about the workflow in doing these kinds of measurements. First of all, here is a stereographic projection showing where the measurements were made on 6 samples. So in each sample, the measurements are made in a plane. The planes map onto the stereographic projection as shown. For each point there, you obtain a time domain signal. And here's a representative time domain signal. You hit the surface with the laser and then watch the surface waves propagating out to tens of nanoseconds. The Fourier transform of that time domain record gives you the solid line on the lower diagram. It has 2 peaks. In this example, there is a true Rayleigh wave and a pseudo surface wave. Now, the true Rayleigh wave has a very narrow width in the calculations that is widened for the time window data that we use. The dashed line represents a theoretical calculation from Green's elastic tensor with the appropriate elastic constants adjusted such that we do fit these peaks. And you can see that the theory matches the experiment quite well. So the process is inverting data to get constants. In other words, we can do a forward problem of given constants, we can predict what the data should be. We need to go backwards to predict what the constants are. And this is a representation of a complete data set for a single composition, 6 orientations, Rayleigh waves and pseudo-surface waves on each orientation. The grayscale background represents the amplitude calculated from the elastic Green's function. Good fit represents high amplitudes matching the location of measurements, and you can see the very light color represent peaks in the theoretical calculation, and measurements are made in regions, well, we observe surface waves at frequencies that match where the calculation showed high intensities. So the details of the inversion, I'm not going to talk a lot about this, I'll just give you a brief sketch. The forward model for determining the Green's function is from Every et al., 1998. And it's a ripple amplitude as a function of frequency at a given wavelength for a line source excitation. The inverse technique involves an optimization, a nonlinear optimization, using what's called in the trade multi-start, using a trust region algorithm, and all of this is to avoid local minimum. In all nonlinear problems, there's a problem of determining whether one is trapped by an optimizer in something that is the best fit or simply a better fit than at surrounding values of the parameters. So not all starting guesses achieve a reasonable misfit. However, a combination of starting in multiple locations and exploring the parameter space achieved a result in which all solutions with acceptable misfit, i.e. the misfit was comparable to our estimate of experimental scatter, gave elastic constants within uncertainties that we give in the paper. Now, surface waves do have an Achilles heel compared to body waves. Elastic constants do not separate as well for surface waves as for body waves. In other words, for body waves, there are certain directions in which a single elastic constant contributes to the determination of velocity. In the case of surface wave, nearly all constants contribute in nearly all directions. So just using surface waves leads to a situation of strong covariance in results. What we need is another set of basis functions, another set of constraints, and Ross Angel measured high precision hydrostatic compressions, which are sensitive to the compliance matrix, the S as an inverse of C, and the X-ray determinations of compression determine components like S1, which is the sum of S11, S12, and S13. So here's how Ross Angel determined these constraints. You measure the strains in directions as a function of pressure. The horizontal scale is pressure, the vertical scale is strain, and there are 6 different strains for this triclinic crystal that you can measure, and the linear slope through those determines a value for the S's. And here are a summary as a function of composition. So these are the 6 S constraints from hydrostatic compression plotted against composition. And you'll notice that there is a clear indication that in the intermediate composition range that there is a change in properties going from the C bar 1 structure to the I bar 1 structure. And we'll look at that in the case of the acoustic velocities as well. So let's talk about the compositional variation of the elastic constants, not for all 21, but for a subset of the 21, the 9 orthorhombic constants. First of all, let's look at the diagonal longitudinal moduli C11, 22, and 33, and those from the inverse matrix, the compliances S11, 22, and 33. These are the elastic constants that emerge from the velocity measurements for each of the compositions and constrained by the compliance measurements from the X-ray single crystal data. And as you look at this, you'll notice that as a function of composition, some elastic constants proceed from albite to anorthite with very little change from the C bar 1 to the I bar 1 structure, whereas other elastic constants show some appearance of discontinuity. And in a detailed examination of the structure, we can show that, in fact, the constants that have discontinuities are the ones you would expect for the nature of the difference in the structure between C bar 1 and I bar 1. Here are the diagonal shear constants, C44, 55, and 66. And again, you can see that some of them proceed reasonably smoothly from albite to anorthite. There are indications of discontinuities for others within the stated uncertainties. And finally, the off-diagonal constants C12, C13, and C23, which vary from albite to anorthite as shown here. Now the interesting thing is that C23 is very close to 0 for albite, but it climbs to a more typical kind of value in the tens of GPa by the time you get to anorthite. In contrast, the other two off-diagonals simply increase from 30 up to 60. When you look at the compliances, you can see, in fact, that the compliance S23 is small for albite and goes down to essentially a 0 value as you increase the anorthite composition. The other two off-diagonal constants, 1, 2, and 1, 3, in the compliance plot are not so different and don't change as much as you go from albite to anorthite. Now let's look at the velocities that are predicted from the full anisotropic set of 21 constants. So these are velocities in an x normal, y normal, and z normal plane going from the axes, the Cartesian axes, not the crystal axes, around in a 180-degree rotation. If this were a orthorhombic crystal, there would be a symmetry plane about the middle at 90 degrees as one goes from the one axis through to another axis. The fact that it's triclinic gives the asymmetry to these plots. We can also plot these velocities in a, let's call it a rose diagram. We plot velocities outward from 0 velocity in the center to 8 kilometers per second at the edge. And I've plotted in grayscale at 2 kilometer intervals changes in velocity. Looking at the upper left plot, we see in the XZ plane for anorthite 0, that's albite. We see the C-axis is arranged vertically. The A-axis is projected at an angle as shown in the dashed line. If this were a orthorhombic crystal, there would be a mirror plane through C, and there'd be a mirror plane through the horizontal axis. And there's, I draw in where orthorhombic crystals would have mirror planes. And you can see that there are deviations from orthorhombic symmetry, but perhaps they are not so large. And you can overall see an imprint of orthorhombic behavior to the elastic constants. And you can see similar trends as you go to the YZ and the XY plane. Interesting on the albite is that the velocities go as high as over 8 kilometers per second for compressional waves, and as low as in the Y normal plane you can see velocities down to 5 kilometers per second. So the plagioclase have very large velocity anisotropy. On the diagram to the left is an indication of how the velocities change on these three planes as you increase the anorthite composition, as you increase the amount of calcium in the structures. And that ends my discussion of the elasticity of the Plagioclase Feldspars.